Welcome Chem 1110 students. We're going to be talking about how we make molecules in this chapter. And this particular video, part 1A, is just going to talk about ionic compounds. A compound in general is a substance composed of two or more elements that are combined in a specific ratio and held together by some sort of chemical bond. I have two examples here. We have water and salt, NaCl, table salt, stuff that we come in contact with every day. But these are two different kinds of compound. Water is a covalent compound. Salt is an ionic compound, and we're going to look at those differences. In order to do that, we use a tool called Lewis dots. And Lewis dots represent electrons on atoms, and yet we know that these dots aren't truly electrons, and it's not the way electrons actually behave, but it's a very useful tool. And we use the dots to represent valence electrons because it's the valence electrons on different atoms that actually interact and form molecules. So to make a Lewis dot symbol, you just take the symbol for the element and you put dots around it representing the valence electrons. So I have an example here of boron. Boron is in it's the third element in the second row. So if you look at its electron configuration, it's 1s, has 2 electrons in it, so it's filled. And the second row, it has a 2s2, a 2p1. And so that's 3 valence electrons. And so for the Lewis dot symbol, we put the B for boron, and we just put 3 dots around it to represent the electrons. You can see it can be in basically any configuration. Here is a little quick picture of the Lewis dot symbols for all the main group or representative elements. And when you look on the right hand side of the periodic table, you'll see that in many cases those electron dots, those Lewis dots, are in pairs, and we're going to talk about that. So if we are looking at boron, carbon, and nitrogen, these are the third, fourth, and fifth elements in the second row of the periodic table. We've already talked about boron, and we know that it has these 3 valence electrons, so there are 3 dots around it. Carbon has 4 valence electrons, 2 in the S and 2 in the P, so you get 4 dots around it, and we look at it as just having the element having 4 sides. But when we get to nitrogen, there's an additional valence electron, 2s2, 2p3, which gives us 5 valence electrons. So this is the first time we form a pair of electron dots. And we're going to talk about the significance of that, but let's not forget about those main group metals, the alkalis and the alkaline earth metals. Sodium's an alkaline metal. It's got 1 valence electron, so it only gets 1 dot. Oxygen, on the other hand, comes after nitrogen, and so it has 6 valence electrons. We pair up, we represent 4 of them in 2 pairs, so then we have 2 valence electrons, and those single electrons show you how many bonds that atom can make. So oxygen can only form 2 bonds with something else. Nitrogen, if you look back up at the top, can form 3 bonds. Carbon can form 4. So the Lewis dot approach really gives us a lot of information about how molecules can be formed. So going back to our example of sodium, it only has 1 valence electron, and that happens to be the 3s1. It's very easy to pull that off if you remember when we discussed ionization energy. And so at that point, you have 1s2, 2s2, 2p6, so you have a closed shell. And so the sodium doesn't have any dots anymore. It just has a positive charge because there's one more proton than there are electrons. Oxygen can also pull electrons from other elements, and so oxygen is a 1s2, 2s2, 2p4 with this 6 valence electron configuration you see on the left. If it picks up 2 electrons from maybe 2 sodiums, then it can get a full octet. However, it's got 2 more electrons than protons, so it has a -2 charge. And we show that by putting a bracket around it and putting the charge outside of it. All right, so we have an example here, and that's to write some Lewis dot symbols for fluoride, the potassium ion, and sulfide ion. And the fluoride then has picked up an electron, and it now has a full octet. We put the bracket with the charge. But potassium, that ion is positive because we pulled the electron off. There are no dots to show, and so you just put the positive charge. And sulfide is similar to the oxide we saw previously. Once again, you've got a full octet of electrons shown by the 8 dots in 4 pairs, and so we put a bracket around that symbol and we put the charge on the outside. There's a little bit of a explanation here, and think about it, that you might want to read. All right, so we're looking at ionic compounds and the bonding associated with that. What we see is that it's not a bond in the true sense of a chemical bond, because the positive and negative parts, the sodium +1 and the chloride -1, are held together because they have an opposite charge, and that's called an electrostatic attraction, and it's an ionic compound. So sodium, you pull off the electron, then the electron can go to the chlorine, making it a chloride ion. And so the sodium ion and the chloride ion, that cation and the anion, are attracted to each other, and it's that electrostatic attraction that holds them together. So in a way, it's a neutral compound, but it's not necessarily a molecule in the sense of a water molecule. But the formula is still 1 sodium to 1 chloride, and so it can be called a chemical compound because it describes the ratio of the sodium to the chloride. However, these things actually exist in a 3-dimensional array, which is called a lattice. And if you've ever looked at salt under a microscope, you know it makes nice little cubes. And the lattice energy is the energy that's released when you put all these cations and anions together. And so we have this reaction shown in something of a picture here with the electron off of sodium moving to the chlorine atom. So you have a sodium cation and a chloride anion, and they can line up as is shown in this cube. They're just the right size to fit together very nicely and produce a nice cubic shape. Very stable, and it releases a tremendous amount of energy when it becomes that lattice because it's very stable. And so, you know, the formation of these ionic bonds releases that energy as it becomes more stable. The higher the lattice energy, or in other words, the more energy that's released, the more stable the ionic compound is. And because of that, it's really hard to get it to melt, because if we think about what melting is, it's when the various particles come apart, they're not held together tightly, and they can move over one another. So for sodium chloride, we have the lattice energy at 787 kilojoules per mole, and a melting point of 801 degrees C. This is not a temperature that you readily achieve in your kitchen, so it's very, very difficult to melt sodium chloride. Okay, what else do we need to talk about? And that is, the last chapter I talked about the importance of the size of the ions, because in order for that lattice to be extremely stable, they have to fit closely together. And the closer they are, the more stable, the larger the energy or lattice energy. So here is a picture comparing lithium iodide, sodium iodide, and potassium iodide. And you can see in the lithium iodide, those lithium cations fit very tightly among the iodide anions. With the sodium, you get a little bit of space between the various iodide anions. And with potassium, which is even bigger because you're going down the periodic table, or down that group, you've got a much larger space, and they're just not as stable if they're not actually touching. So the lithium iodide has the largest lattice energy. It's the most stable, whereas potassium iodide is the least stable. Okay, in 1B, we're going to talk about molecular compounds.